Hello, my name is Steve Klotz. I work with JDSU and MedusaLabs, and I wanted to talk today about debugging a data corruption in a trace. It's a question we kind of get often about how to find LBAs and how to look for things. So I'm going to show you some features that you may not know exist, and show you some features that are not in your version yet that are coming out soon that'll help you along the way to do this. So I captured a corruption here. We've got the trace file, and we have a bad file produced. Corruption was generated using MedusaLabs Test Tools. The MedusaLabs Test Tools are pretty verbose about helping you with data corruption. Hopefully whatever tool you're using is too, because just saying there's data corruption is pretty helpless. So we've got a log file here in the trace. I'll go ahead and open up the trace real quick, get that going in the background. We're using an interim version of TraceView right now because I want to show you a new development feature that's coming out soon. I'm going to go ahead and run Expert. Expert's going to do a lot of nice features for us in the background. We'll just go ahead and let that run. In the meantime, I'm going to look at this log file. In this log file, it basically tells us that we wrote this value, read this value here, and this was the offset within the buffer, and this is the offset on the disk, the absolute offset on the disk. And we can go down, there's all kinds of information in here we'll need to know. There's the drive, which in Windows space is named by a physical drive moniker, and we're going to need to translate that to a fiber channel address. It tells us what LBA it's at and what offset within that LBA. So we're at LBA 800 and an offset of 1B00. So if I go up here, click this out, go up here and take 1B00, and we divide that by the number of bytes per sector, which in hex is 200, or 512 bytes per sector. We're going to get a D8, so it's LBA 800 plus D8. So we're looking for LBA 8D8 in this trace. It's the corrupted one. And the Medusa tools always do a write followed by a read, then a write followed by a read to a given LBA. So that'll make it very nice and consistent for us to debug. And we can see here it does after the corruption, it does a retry. So we should see a write, a read, and a read. Let's get into the trace here. Expert has processed the trace and done a nice little job in the background for us of helping us with a lot of things. We'll come back to Expert in a minute. In a basic trace view, you have this new exchange view, which has come up in the last versions. We do exchange view for iSCSI, SAS, SATA, and fiber channel SCSI traces. And Expert has done things for us like build this exchange view. And it also does things. The exchange view contains the command. It contains basically a list of exchanges, their exchange completion time, how long they took. That took this is in microseconds. So that took 2.7 milliseconds. You can see how long each exchange took. Each line represents one SCSI exchange. If we expand it out, we can see the read capacity, and then you can see the data that came back with it. And Expert does some other subtle things in the background, one of them being, like here, it puts a tag on this frame. So TraceView knows to decode that as a read capacity data frame, so that you have that decoded and you don't have to get out a book and find the spec and figure out what read capacity data format is. So anyway, you have one line per exchange, and you can expand them out in exchange view. We'll come back to exchange view in a minute though. So here, let's look at the trace. The Medusa test tools write a trigger when they find a data corruption. It's an option we have set in them. So they're going to write a trigger to the drive. I've got this trace was just a JBOD of drives. So there's just a bunch of drives out in here, and we can look at the topology in Expert and see that. There's drives out on several switch ports here. Excuse me. And so there's a bunch of drives in here. I need to isolate first the mapping between physical drive 11 and that drive. To do so, I'll just use the trigger, and my trigger is going to end up on a frame here, and basically that's the Medusa test tools trigger. We tell it to write that whenever it goes in there. So there's my trigger data frame here, and I can basically double click the source destination now, and I want to filter for that destination. That's the drive I'm concerned with. Clear whatever's in my filter list from previous usage here. And now we can use a real nice trick. we can go in here and use this new feature in LBA. If you ever see a frame in TraceView that has something you want in it, like a LBA there, just double click on it and it pulls up this dialog. Now you have a field chooser in here. You can choose all kinds of different methods for how you're going to find the data and what you're going to find. So let's look for the LBA. Let's just do a field filter for LBA. And notice it gives us this new value. This won't be in your version. It'll be up in version 5.4 soon. And the new comparator is to search for LBA range. This would search exactly for LBA 400. This would search for anything containing LBA 400. Like, for example, this LBA 400 here goes from 400 and transfer length to 100. So it covers from hex 400 to hex 500. So if there was something at 455 in the middle or 4AE, it would be contained and found in this search. Similarly, we were looking for LBA 8D8, right? So I'm going to go look for LBA 8D8 here, and I'm going to go ahead and just filter for that. And I'll apply that. That stacks the filter on top of the filter I already have. So we've combined these together. We've got for that target and this LBA. And in here now we can see what's going on. Now again, I said the Medusa test tools, and this may be different for your tools, is write and read. Given a sector, they will write and read it continuously. And then when they find a corruption, they will send the trigger and then retry the read. So we have a retry read here. We have the last read. We have the write. And now I'll go ahead and mark the previous one too, because they might be interesting to us. And in here, now we have basically the commands. Now we can do old school way. We can sit there and take that write command and very simply filter. And I need to go back to this filter list. I need to remove that because I don't want that LBA filter in here anymore. I'm just going to filter for this OXID. Actually, I could do another trick here. That'll be easier for me. I can filter for, I can hide OXID so I don't have to worry about my filter set. I can just create a hide set. Hide everything that's not equal to that OXID. And now here's the write. And then all we do is go down to offset 1B00. And we can look at the data. Now, this data is being written out. Does that match what we were saying? Let me reduce this down in size here. Let's go to the top. And yes, that matches what we were saying. It's basically the data within here. Okay, so there's a write. Let me go ahead and bookmark that. Okay, data. Now the other way we could do this, clear this out, so we can use our exchange view instead. I can go to my write here and simply say, go to this exchange and exchange view. Now I can just break it out. So I can use this as a navigational path here. And I can go down to that frame that's 1B00. And there it is, and now I can see the frame down here. So that's a nice convenient way to do that, and we'll do that for the read. Let's go look for the read. Read, go to the exchange view, and we can expand him out and go look for that same offset again, 1B00. And now there's our incorrect data. So we can see that we wrote the correct data, and here's what we read back, and it's incorrect, doesn't match. I personally wonder where that data came from, so that's why I bookmarked the previous read and write. I want to see what he actually put on the disk in the previous I/O. Maybe this is just stale data here. So if I go back to the previous read, find that in exchange view, you'll notice exchange view syncs one way. Well, let me finish the example first. So read, let's go back to 1B00. There, and there is the exact same data that we got on the second time we read after we had written to it. So we wrote, read, got this, then we wrote again a different pattern and read and got this old stale data back again. So apparently the drive forgot to commit this chunk of data to the disk. Probably not a real acceptable thing. What I was talking about was synchronization between these two views. We call this the grid or event view, and this is the exchange view. They each have their own filters. So if I set a filter here and it's not going to apply here, if I set a filter here, it's not going to apply here. They each have their own filter state. You got to watch the buttons. So like there's a filter applied there, like over here, there's no filter applied. To synchronize them, from grid view to the exchange view, you right click and you say go to this exchange. To synchronize this way, you can very simply just turn on this button, and anytime you click here, it will move you. It'll move you to the exchange in question there. Okay, so that's a nice synchronization option there. And we go in here. A couple other things to note out real quick. Let's look at this. So expert. Let's see if they have any explanation, because we have this nice. We have write, read, write data, read, and then corruption, and then a retry. We can go check our retry. Actually, let's do that too real quick here. Exchange view, the retry, 1B00. Yeah, and it's the bad data again. So it obviously got written to the disk improperly. Let's go look and see if expert gives us any clues as to what's going on here. So expert has parsed the trace and gone through all the rules that it can think of, and it's found a couple of things. And this one kind of stands out like a sore thumb. There's a check condition missing sense data, and it may not seem related to this, but there's something that's very strange. It's required by SAM, the SCSI architectural model, to return sense data. You have to do auto sense today. And so to not do auto sense is a very strange thing. So that's why it comes up as an error. So let me go look at this. Let's just go ahead and go to trace view, and here's our check condition. Oh, and notice that's on the same drive, 6604E2. It's on the same exact drive that we were using before. We filter for that drive again. Clear out whatever's in here. Filter that. Go ahead and turn off this exchange view for now. So we have a write followed immediately by a check condition on this OXID. It's very, very strange. And the write, there's nothing weird with it, and the check condition is violating SCSI. It doesn't have the sense link data to it or anything to it. It's followed up, and the initiator says, well, what just happened? I need my sense data. And so it does a request sense, which is obviously a sign of a problem here. And then the drive comes back. It's obviously brain dead, and it says there's no sense information. So this drive has gone off on a ditch somewhere here. This is very strange behavior. I'm going to go ahead and bookmark this just to see one simple trick. Where does this fall within the pattern of things here? So we did the write data, check condition, then we did the read, and we got a corruption. This drive lost its brain somewhere, is what happened. We can also look for other clues in here, and there's an abort sequence. It's on a different drive though, so that's probably going to be a different issue. I'll go look at it, and maybe another drive losing its brain there, but that doesn't make sense at all. Not much else in here that really ties to it, but that's kind of a critical piece to this clue, is why this drive just randomly came back with that check condition right in the middle of where it was about to corrupt. That's not a coincidence at all. Okay, quickly, other utilities you have for debugging data corruptions in trace view. In this double click, there's a sliding search. So you can search or filter on a hex value. So if I wanted to find everywhere that data pattern was used on that drive, because I have in my quick filter list just that drive, I'll just add that to my filter. And so I can see all of the exchanges and places and times where it's been used. That's a real nice search. It's really powerful. So if you have a unique data corruption or something you're searching for in the trace that's a simple hex word, you can search that way. The other way you can do it is through this detailed find filter, which gives you a lot more powerful way to do it. And I'm going to go in here and just put a find in for any frame. And you double click on this, and it has a containing tab, and you can put anything you want in this value. So you can put a whole row of values in there to search for a blob of data that was in your corruption, or something you found that's something that's unique to you, and that will help you do a find. That's a very powerful and useful tool for doing a find. And all of the examples I had here can be done in both exchange view and in the grid view. You can do it both ways. So there's a good set of tools for helping you out debugging corruptions, and hopefully that'll help you out along your way. Thanks.